Hello and welcome to this video where we're going to take a deep dive into strings in Go. Now we're probably going to cover some topics that I haven't touched upon yet in the videos. Don't worry, stick with it, it will all make sense. I'll explain what I need to explain for this video, and then in future videos I'll cover the more advanced topics. And if you want to, you can always come back to this video and have a really good understanding of strings in Go. Let's start with the basics then. In Go, a string is a built-in type that represents a sequence of bytes. Notice that I said a sequence of bytes and not characters, as this is a distinction that is going to be really important. If we take a look at this simple program that I've got in Go, you'll see I create a string of hello, and then I just print out the length of that string. If I run this, we'll see that we get 5. And we know this because, as we covered it in the last video, when we print out the length, we print out the length in bytes of the string, not the length of the characters. And you can see that with the signature of the function. So for a string, the number of bytes in V. And this means that this string length is 5 in terms of the bytes of the string. Internally, a Go string consists of two parts. You have a pointer to the underlying byte sequence. You then have a length indicating how many bytes are in that sequence. Let's take a look at a diagram to help explain this. So here we have a diagram of how strings are stored within Go. You have the string header and you have a pointer, which is a reference to the first byte's location in memory. And you then have a length. So if we think about how this string is actually stored in memory, in your memory, you will have a sequence of bytes. So you'll have the characters H, E, L, L, and O stored in binary in your memory. So you'll have this sequence of bytes here. And each of these bytes will have its own memory address. In this case, we're saying that the character H, or this representation in binary, has the address of ABC123. And this byte sequence represents the whole string. So in Go, the string header for our string S here will have a pointer to this memory address, and it will have the length of 5. So this S here actually represents the header, and the header will know that it needs to get all 5 bytes because of the length, and it knows where to start because it has a pointer to the address of the first character. And as we know, this is a contiguous sequence of bytes that are stored in memory. So this means that the string variable S is just the header containing the pointer and the length, while the actual bytes are stored separately in memory as a contiguous sequence. For string literals like hello that we've created here, the compiler stores these bytes in the program's read-only memory section, ensuring that they cannot be modified. For strings created at runtime from user input, file reading, or concatenation, the bytes are stored on the heap and are managed by Go's garbage collection. We can start to verify some of this behavior. So I'm going to take this script that I've got here. I'm just going to paste it in. Don't worry about the code. It's more about the behavior of the code that's going to be interesting here. So let's start off with two string literals. So I've got two string literals here, both with the hello. Let me just comment out the rest of this script for now. So all I do here is I've got the two string literals of hello, hello1 and hello2. I then grab the pointer to the underlying byte sequence. So it's going to be the first byte. In this example here, it's going to be ABC123. And I'm just going to print out the pointer itself. If I go ahead and run this, you'll see that both hello1 and hello2 have the same address in memory. So this here is the address to the first byte in this byte sequence, which is ultimately in this string header here. So this is going to be the pointer to the first byte. And because this is a string literal, and Go is a very clever language, what it will do when it compiles this, because it is the same string literal and strings are immutable, as we'll see in a bit, it basically shares the same address in memory. There's no point in creating the string and storing it twice in memory. It's exactly the same, so the compiler makes this optimization and it uses the same memory address and the same underlying byte sequence. So the data is shared in this case. If I go ahead and create a new string through string concatenation, so I've got this hello world string here, which takes the first hello, and I then concatenate the string space world onto it. Again, I then go ahead and get the pointer, so the address to the first byte in that sequence. I then go ahead and print out that particular byte. We should see that we get a new address for number 3. And we can see here that we do. So again, hello 1 and hello 2 share the same address. And then our hello world, which was created via string concatenation, is a new address. And we know this because, as we said before, when you create a new string via concatenation, the bytes are stored on the heap and they're not in the program's read-only memory, which is what happens when you create a string literal. So this is going to be stored in the read-only memory, and this is stored on the heap. We can also have a look at what happens when we do the same sort of thing with a substring. So let me uncomment this code here, and we can talk through it. So you can see I've got a string of hello3 here, and I get a substring from the hello world string concatenation that we had earlier. So this is going to grab the hello or the hello1 from that particular string. It's then going to get the address, the pointer to that first byte sequence. We're then going to print out the pointer for hello3, the substring, and we're also going to point out the pointer for the whole hello world string. So we can see here what happens. So in the substring, we get exactly the same address as we do for the hello world, right? And they're the same substring, right? Because the substring shares the memory with hello world. There's no point in creating a new hello for this particular substring. We're just grabbing the first byte and then the subsequent 5 bytes from that. And of course, it's from the same point in memory, so we just print it out. So basically, you can think of it as we're saying for our substring, just grab these 5 bytes and print those out. And finally, we can also check the length of these strings. And again, as we know there, because they're a sequence of bytes, it is ultimately going to print out a length of 11 and a length of 5. So our hello world is obviously longer than the word hello, and obviously this has more bytes than the simple hello. So hopefully you can see here that when you create a string literal, if it's the same string literal, the compiler will optimize it and store it as the same byte sequence. So this string here will be the same underlying byte sequence for both. You can see that when you use string concatenation, we create a new string. And you can see that when we use substrings, we grab it from the same memory address. We don't create a new substring. We just reference where the existing substring is in memory. If we go ahead and have a look at what actually happens in memory when we do string concatenation. In this example here, I've got A, which is hello, and B, which is world. If I create a new string of C, which is a concatenation of both A and B, what we'll end up with is something like this in memory. So we'll have the string header for A, and as we know, that's the pointer and the length. In this case, it points to the byte sequence for hello. We will have the string B, again, pointer and a length. And in this case, it's going to point to the byte sequence of world. And then we'll have header C, and this is going to be a new allocation, so a new bit of memory. And that's going to be a new string, which points to an entirely new string of hello world. So when you do string concatenation, you are creating a entirely new string. And so a completely new byte sequence is allocated for the concatenated string, hello world in this case, and the original strings remain entirely untouched. One of the most important characteristics of Go strings is that they are immutable. Once created, you cannot change individual bytes within a string. If we look at this example here, we have a string S with a lowercase h. We cannot go ahead and edit the first index of that string and capitalize it. This is going to give us a compiler error. And that's because strings are immutable. If you wanted to do something like this, what you'd have to do is use string concatenation. So you'd have to create a new string, a new byte sequence in memory. And in this case, you'd be creating a byte sequence with a new capital H, and then you can copy over the sequence of characters E, L, L, and O. If you go ahead and run this and print that out, you'll see that we get the correct string here. So the important thing to know here is that in Go, strings are immutable. If we take a look at how that looks in terms of our little diagram and string headers, You see here we've got the header again, we've got our sequence of bytes, in this case hello, and as we know it's immutable, so we cannot modify this byte at all. We have to go ahead and create a new string if we want to do that. And this immutability gives Go some significant opportunities to optimize in terms of the compiler. So if we take a look at this example here, let's create a string of s1, which is going to equal hello world. And let's create a string of s2, which is going to use a substring of s1. So this is going to take the first 5 bytes of our first string. So this is going to be basically the text hello. If we go ahead and just print this out, we can just do printf and we'll just do s2. We'll see here that we do get the string hello. Now let's visualize this as to how our two string variables can share the underlying byte data at this point. So we've got our first string here, s1, which is hello world. And in memory, you're going to have s1, the header. You're going to have the pointer, which points to the first byte of our byte sequence, as we know, which in this case is going to be the binary for the letter H. And we have the length, which in this case is 12. We then have our new string from the substring, so s2. And in this case, we're going to have our s2 header. But because this is just a substring, Go doesn't need to allocate any new memory for this particular string. It can just reuse the existing hello world string, the existing byte sequence, right? And it can do this by just pointing to the first H byte and using the length of that. And using the length of that string, as it knows it's 5. So you can imagine that somewhere in our memory, we have this byte sequence here of hello world. When we do this substring here, rather than creating an entirely new string, what we can just do is for S2, we can just point at the first byte here, because we know that's the same string, and then say it's going to be length of 5. And that's just one of the nice optimizations that we know we can do in Go because strings are immutable. You can imagine that if strings were mutatable and we did something like this, and then I go ahead and change this string to be an A, for example, that not only would change the S1 string to be incorrect, it would also change the S2 string because they point at the same memory address, the same byte sequence. But because strings are immutable in Go, we don't need to worry about that. And it's all going to work as we need it to. Again, we can prove this behavior with some simple code. So again, we've got our S1 string here of hello world. We've got our S2 string, which is the substring of our S1 string. So just the byte sequence for hello. I then grab the pointers for both of these here. So the pointers for S1 and the pointer for S2. And then it's going to print these pointers out. So we should get exactly the same memory address here. And we do. So again, this means that our S2 string is just pointing to the start of this byte sequence here. And because it has the length, it can just reuse that particular byte sequence. If you come from a language like C, you might be used to seeing things like null terminators. Well, in Go, unlike C, we do not have the null terminator. Strings, as we've seen, explicitly track the length. So we have the length in that header. Go strings can contain any bytes, including null bytes. And as we said, strings are immutable. They cannot be changed once created. If we just look at a quick comparison from Go to C. So in C, when you store a string, you store the sequence of bytes, and then you have what's known as a null terminator. And that's how C knows that the end of the string is at that point. In Go, we don't have that null terminator. We keep track of the length of strings in the header with the length property. As we've seen, we don't need to have null terminators. And this means that the byte sequences in Go are truly read-only at the hardware level. And as we said, the way that Go does this for string literals is it places the byte sequence in the read-only data section of the binary, which we'll see in the future. And for runtime strings, it allocates them on the heap. But one thing it doesn't is it never provides any methods to modify them. And as we've seen, that makes strings truly immutable. Now for something crucial. as we said, Go strings are not Unicode strings, they're byte sequences. However, Go was designed with excellent UTF-8 support, and UTF-8 is the default encoding. UTF-8 is a variable length encoding scheme for Unicode. ASCII characters are represented as single bytes, while other Unicode characters require 2, 3, or 4 bytes. And we can see this in an example here. So we have an ASCII character, capital A, and then we have some Unicode characters here. I'm just going to go print the length of each of these out. So you can see that the A character, the ASCII character, has only 1 byte, whereas the other Unicode characters have up to 4 bytes. So we've got 2 for this E with an accent. We have 3 for this Chinese character, and then 4 for this character here. I don't know what this character actually is, but it's got 4 bytes. And this ultimately has some interesting implications. Let's look at what happens with non-ASCII characters. So I've got this code here, and I've got 2 Chinese characters. I don't know what they mean, but it's going to be useful for this example. If I go ahead and print out the length of these bytes, you'll see that it's 13 and not 8. And that's because visually this string only has 8 characters, but the bytes are 13. And that's because the 2 Chinese characters each require 3 bytes in the UTF-8 encoding. Let's have a look at what this actually looks like in memory for that hello with the 2 Chinese characters. You'll see here we've got the characters, we've got hello, and then those 2 Chinese characters. You'll see the hex representation of the bytes. You'll see here that for hello, each one is a single byte. Whereas for the Chinese characters, the first one is 3 bytes, and the second one is also 3 bytes. If you look at the indices of these, you'll see that for hello, it's 0 to 5, whereas for the Chinese characters, it's a sequence of 3. So 7, 8, 9 for that one, and 10, 11, 12 for the second one. And if we were to iterate through these, we would end up with a range index of 0 to 7 to the first character, the first Chinese character, and then 10 for the second character. And we can verify this with the code itself. So let me just run the code that does this. So what we're doing here is, again, we've got this simple string, hello with the 2 Chinese characters. We then print the length in bytes. So again, we should see 13 rather than 8. If we then print each byte with its index, again, don't worry about this syntax. You'll kind of see what it means as we go. And then we print each rune with its byte index when using the range. This might seem pretty complicated, but let me just run the program and we'll start to see what's actually going on. So we can see that with our byte indices, we go from 0 to 12, and we have the actual hex of those particular characters, right? Whereas with the runes, we have the byte index, and we go from 0 to 7, and then we actually jump from 7 to 10. And that's because with these 3 characters, again, we have 3 bytes rather than 1 byte. So for this first example, we're just iterating through the bytes themselves, and we go from 0 to 12, going through each particular byte. So in this case, 7, 8, 9 is the first Chinese character, and 10, 11, 12 is the second one. Whereas when we use runes, we go from 0 to 7, and then 7, 8, 9 is included in the full character, as it's UTF-8 at this point. And for 10, we just make that jump. So you skip the ranges when you're using runes. You go through the full byte sequence for that particular character, which is quite useful to know. And this is where the rune type itself comes in. A rune in Go is basically an alias for the int32, and it represents a Unicode point. And to understand this, let's have a look at some examples. So here I've got a rune type, and again, it's this Chinese character that we saw earlier. And I'm just going to go ahead and print the type, the value, and then the Unicode representation of that string, and we'll see what we get out. So you can see the type of this rune is essentially int32. And as we said, a rune is basically an alias for int32. We then get the value. So that's going to be the integer value of the rune. We then get the Unicode representation. So that, if you Google that, you'll find that it represents this particular Chinese character. And as we know, when you iterate over a string using Go's range loop, it automatically decodes the UTF-8 bytes into Unicode runes. And we saw that earlier, but let's take a look at another example just to clarify that. So we've got this code here, we've got the hello string, and we're going to iterate over it again, looking at the byte position, the rune, the Unicode, and then the bytes themselves. And what we'll see here again is the byte position, or the indices. We go from 0 to 7, as they are all ASCII and a single byte. When we get to the Chinese characters, they're 3 bytes, and we jump from 7 to 10. The runes are the actual Unicode characters themselves. You can see the Unicode representation here, and then you can see the actual bytes. And you'll see it's 1 byte for each of the characters in hello, and then the space and the comma. And then you'll see that for the Chinese characters, it's 3 bytes each. And that links up with the position here from 7 to 10, it's 3 bytes. Take a look at how this actually looks in memory. So again, you've got this byte sequence here of hello, comma, and then the bytes for the particular runes. So you've got the individual ASCII runes, and they are 1 byte each. You then have the Chinese characters as a single rune, and these are 3 bytes each. And if we were to convert this string into a slice of runes, we would go from 13 bytes. So that would be each of the bytes plus the 3 bytes for the Chinese characters, as we see here, 13 bytes. To runes, we would end up with 36 bytes in total. And that's because runes are actually 4 bytes per rune. This is because when you convert a string to a slice of rune, Go decodes all the UTF-8 sequences into Unicode points. Again, we can have a look at this with a code example. So let's just look at what we're doing here. So again, we've got the hello with the Chinese characters. We've then got our runes here. This is just a slice of runes from our string. We print the length of the string, which is going to be 13 bytes, as we know. We then print the length of the runes, which is going to be 9 characters long. Let's go ahead and just run this and verify that that makes sense. So yes, as we can see, when we print the length of the string, so the byte sequence, it's 13. When we have the runes, it's 9, because that's the length of the runes themselves, the characters themselves. And we can now access these via the character index. So in this case, it's going to be the 7th index here. We get the correct character. If we go ahead and change this to be the 8th character, sorry, the 8th index, we'll get the other Chinese character. And then if we do 9, we will end up with an error, because it's going to be an index out of range error, because it's no longer the sequence of bytes, it's the sequence of runes. And so ultimately this conversion allocates a new slice of int32 values, which uses 4 bytes per character, regardless of the original UTF-8 size. And this is often much more memory intensive than just using the byte sequences, but allows random access to characters by index, which isn't possible with the original string. And we can just prove that again. So if we run this with a printout of the runes and the 7th indices, so we should get the Chinese character 7. But if we change this to be the string, so the actual byte sequence itself, and we print that out, we're going to end up with something that's incorrect. Oh, we need to get rid of that. We're going to end up with a strange character, which is going to be this weird A character. And that is ultimately because this A will be a integer. So we can print that out and we'll get the integer number, which will be 288. And if we look at the ASCII table, we'll probably find that that number represents that particular, So if you look at here, the ASCII table 288 is that weird A character. And that's because when we are accessing via the strings, what it's actually doing is grabbing the first byte of this Chinese character, which is going to be 228, and then just converting that to ASCII. So you can see that when we use the runes themselves, it works nicely when you access the characters via the indices in the index runes. Because Go stores strings as raw bytes, indexing a string directly gives you the bytes, not the characters, as we've just seen. This can lead to some bugs if you're not careful. So for proper character or rune handling, you've got a few options, and we've seen one of them already. So the first one is you can convert it to a rune slice for random access like we've shown already, or you can use the UTF-8 decode rune in string function here. We saw that again in the basic types video. Or as we saw earlier, if you're doing sequential access, you can use the range loop in Go, as that will convert them to runes for you. And again, if we just run this program here, we'll see that we get what we expect. So on the first one, because it's now a slice of runes and we access via the random access, we get the character correctly and not the byte. Equally, when we use decode rune in string, we get the character itself, and we can also grab the size of the character in bytes. And then again, for the range loop, we can grab the index, the rune itself, the bytes, and the Unicode representation. And again, we've seen how the range index works on that as well. So there's 3 ways that you can handle that. And it is important to know that accessing strings via the raw bytes can lead to bugs. So watch out for that. You will probably run into it at some point, but just remember that strings are sequences of bytes and you need to convert them to runes. And with that, I think we've gone deep enough into strings for now. So hopefully you now understand a bit more about how strings are actually stored in Go and how to use them. You also know that there are a few gotchas because they are stored as byte sequences and not as the characters themselves. So hopefully you can avoid that in your future Go programs. Thanks for watching. If you've liked this video, please do hit the like or subscribe button, as it does really help out the channel. Thanks for watching.